In this video, we're going to talk about the gas laws. Now, in order to talk about the gas laws, we first must understand the different properties of gases. So the first property we're going to talk about is pressure. And pressure is how often and with how much force a gas molecule or gas particle is going to hit the side of the container. Now, pressure has units of atmospheres or millimeters of mercury. And there are 760 millimeters of mercury in one torr. This should be atmospheres. Sorry about that. In my head, I got it confused because there is 1 millimeter of mercury in one torr. In this video, we are going to talk about the gas laws. Now, in order to talk about the gas laws, we must first understand the different properties of gases. The first one we're going to talk about is pressure. Now, pressure is how often and with how much force or energy a gas molecule or particle hits the side of a container. Pressure is measured in atmospheres or millimeters of mercury. In the United States, we use inches of mercury. 1 atmosphere is equal to 760 millimeters of mercury. Now, another really common unit of pressure is the torr, and 1 millimeter of mercury is equal to one torr. So that means 1 atmosphere is also equal to 760 torr. The second property we're going to talk about is the volume. Now remember, the volume of a gas is going to be equal to whatever the volume of the entire container is. Gases do not have a fixed volume. They're going to take up the entire volume of the container. The third property is the amount of gas, and this is usually given in moles. Now, most of the time, when we are measuring the amount of something, it's in grams. So you're going to have to convert your grams to moles. And then finally, we have temperature. If you manipulate the temperature, then you can manipulate how fast or how slow the gas particles are moving. And in turn, you can manipulate the pressure and volume. STP is standard temperature and pressure. So that's what STP stands for. And the standard temperature is 0 degrees Celsius or 273 Kelvin. And the standard pressure is 1 atmosphere. So what that means is at STP, 1 mole of gas has a volume of 22.4 liters. And that is referred to as the molar volume. Just like molar mass is grams per mole, molar volume is liters per mole. We are going to talk about 4 simple gas laws where we just evaluate 2 of the total properties, and then we're going to combine them to get the combined gas law, and then we will talk about ideal gases. So the first one we're going to talk about is Avogadro's law. And Avogadro's law is where pressure and temperature are held constant. So the 2 things that are going to be manipulated or varying are the volume and the amount of moles. So volume And moles, or N, are directly proportional. So what that means is if I increase my volume, and when pressure and temperature are held constant, then I must have increased my moles. The equation for Avogadro's law is V1 over N1 is equal to V2 over N2. In Boyle's law, the temperature and the amount, so T and N, are held constant. Pressure and volume are inversely proportional. So the equation for Boyle's law is going to be P1 V1 equals P2 V2. If you hold volume and the amount of gas constant, then you're dealing with Gay-Lussac's law. So Gay-Lussac's law is where pressure and temperature are manipulated and they are directly proportional. So if I increase the temperature, my volume and the amount of gas are held constant, then my particles are going to start moving faster. And if that's the case, they're going to hit the side of the container more often and with more energy. So it will increase my energy. The equation for Gay-Lussac's law is P1 over T1 is equal to T2 over T2. Finally, we have Charles' law. And with Charles' law, we are holding constant pressure and the amount of gas. So we are manipulating the volume and the temperature. And the volume and temperature are also directly proportional. So the equation for Charles' law is going to be V1 over T1 is equal to V2 over T2. Now, you do not have to memorize these equations. They will be provided for you, but that doesn't mean you can't do the practice problems. You have to make sure that you are getting practice with using these different equality or equations. So here is a great table from your textbook that shows how the different properties of the gases are related to each other for the different laws. All right, let's get some practice using these gas laws for problems. When you are doing these problems, the very first thing you're going to want to do is decide which variable or which gas law you're going to use. In order to do that, you need to look at your units. Your units will tell you which properties of the gases you are using. As soon as you figure out which properties you're dealing with, then you can figure out which gas law you're going to have to use. So, after you figured out your gas law, then you need to decide which variable you need to solve for and isolate that variable. Finally, you can solve. So plug your numbers in and solve for that variable. So in this first example, what I like to do is just write out all of my numbers with units. So the first number I see is 3.9 liters. This is a volume. The second number I see is 20.7 spheres. So this is a pressure. And then finally, the last number I see is 1.0 atmospheres, which is also a pressure. In this problem, I'm only dealing with pressure and volume, so I need to go back to my gas laws and look at which one only has pressure and volume. Avogadro's law has volume in moles. I don't have moles, so I can't use that one. Boyle's law, look at that, pressure and volume. So this is the gas law I'm gonna have to use. So Boyle's law states that P1 V1 equals P2 V2. Now I need to assign variables to each one of my numbers so that I can figure out which variable I'm trying to solve for. So if a tank contains 3.9 liters, this is a volume, and this is what it starts off with. So this is going to be my V1. It has 3.9 liters of oxygen at 20.7 atmospheres of pressure. So this is the pressure it starts off with. So that's going to be my P1. Now, when I keep reading, it says, what volume would the gas occupy? So that is my question right there. That tells me what it is that I'm trying to solve for. So what volume? I already have V1. So this means I am solving for V2, and my P2 is going to be 1. So since I'm solving for V2, I can rearrange Boyle's law to solve for V2. So V2 is going to be equal to P1 V1 over P2. Now I have a plug and chug situation where I can take the numbers for each variable, plug them into my equation, then chug it out on my calculator. So P1 is 20.7 atmospheres. V1 is 3.9 liters. P2 is 1 atmosphere. Notice that when I cancel out all of my units, the only units that I'm left with are units of liters, which is good because I'm solving for volume. All right, when we plug this into our calculators, we can take 20.7 and multiply it by 3.9, then divide it by 1. And I get V2 is equal to 80.7 liters. All right, let's look at our next example. I'm going to do the exact same thing. 7 liters, 25 degrees Celsius, and then I have 77 Kelvin. 7 liters is a volume, 25 degrees Celsius is a temperature, and 77 Kelvin is also a temperature. So I need to find the law that relates temperature and volume. We go back to our gas laws. Charles' law relates temperature and volume. So we're going to be using the equation V1 over T1 is going to be equal to V2 over T2. So now I need to assign all of my variables. So I have a balloon that has 7 liters. It has a volume of 7 liters. That's what it's starting off with. So my V1 is 7 liters. And that balloon is at 25 degrees Celsius. So that is my T1. If it is dipped in liquid nitrogen that has a temperature of 77 Kelvin, that is my T2. And the question, what is the volume? B2 is what I'm trying to solve for. So I can rearrange my equation for V2, and I get V1 times T2 over T1. This is a plug and chug situation. I want you to be very, very careful about this. If I plug this in as I have it written, will my degrees Celsius and Kelvin cancel out? No, they won't. So I need to make sure they're both in the same unit. This is very important. All gas laws use Kelvin. So what that means is temperature must be in Kelvin. And the reason or the reason this is true is because if you're dealing with 0 degrees Celsius and that's your T1, what's going to happen if you plug that into T1? That math is not going to math. You can't do it. So you always want to be in Kelvin. Kelvin does not reach 0. So before I can plug these in, I'm going to have to change my degrees Celsius to Kelvin. And we do that by adding 273. So this is going to be 298 Kelvin. Now I'm ready to plug this into my equation. My V1 is 7 liters. T2 is 77 Kelvin. And my T1 is 298 Kelvin. Notice my units of Kelvin cancel out. I'm left with liters, which is good because I'm trying to solve for volume. When we put that in our calculator, I can do 7 times 77, get that answer. I get 539, and then divide by 298. So my volume is going to be 1.81 liters. Now, does this answer make sense? I know that when I'm relating volume and temperature, that they are directly proportional. So if I increase my temperature, my volume should increase. In this case, I decreased my temperature by quite a lot. And as you can see, our volume also decreased. So this answer makes sense. All right, let's try a couple more. What is the resulting pressure? Ooh, right away, I can tell that resulting pressure, this is my P2. When a tank is filled with argon gas at 0 degrees Celsius, so I'm starting out at this is my T1. I have a red flag right now. What do we have to do? You got it. We need to convert this to Kelvin. So this is going to be 0 degrees Celsius plus 273, which gives me 273 Kelvin. So I can continue reading and see what else we are dealing with. So we have a tank filled with argon at 0 degrees Celsius at a pressure of 0.33 atmospheres. This is my P1. This is the pressure that is associated with my T1. This is the pressure that it is starting off at. Now, if we heat that to 75 degrees Celsius, it's my T2. And what's going off right now? Yep, got to change it to Kelvin. So my T2 is going to be equal to 75 plus 273. Go ahead and put that in your calculator. What do you all get? I get 348 Kelvin. Now I know that I only have pressure and temperature. I can look for the law that relates pressure and temperature. And that is going to be Gay-Lussac's law, and it is also directionally proportional. It has a direct relationship. So the equation I'm going to be using is T1 over T1 is equal to P2 over T2. Notice in all of these gas laws, temperature is on the bottom if it's one of the variables. So here, temperature is on the bottom. Also with Charles' law, temperature is on the bottom. We already figured out that we are solving for P2. That was my question. What is the resulting question, or what is the resulting pressure? So if I solve for P2, I'm going to get P1 T2 over T1. And now we have our plug and chug situation. T1 is 0.33 atmospheres times T2, which is 348 Kelvin, divided by T1, which is 273 Kelvin. Now, pressure and temperature are also directly proportional. So if I increase my temperature, which I'm doing here, then I should also see an increase in pressure. So plug this into your calculator. We can take 0.33 times 348 and then divide that by 273. And I get 0.42 atmospheres. Does this answer make sense? I increased my temperature. I increased my temperature. So I should see an increase in pressure. And I do, because I started out at 0.33 atmospheres, and my final pressure is 0.42 atmospheres. All right, let's look at this last one. This last one is a little bit more tricky because I have 5.3 grams of helium. None of my laws deal with grams. So what you need to realize is grams of a gas particle is an amount of that gas particle. So we can use the grams to calculate the moles. And we can do that using the molar mass. So if you don't already have one, make sure you get a periodic table in front of you so that you can easily access the molar mass of these different substances. So we have 5.31 grams. I know I need to calculate the number of moles because moles is one of the property of gases. Well, moles is one of the properties of gases. So 5.3 grams of helium times 1 mole over 4.00 grams. And when I plug that into my calculator, I get 1.325 moles of helium. Now, this is what we're starting off with. So that tells me this is my N1. A balloon is filled with 5.3 grams of helium to a volume of 12 liters. So that's what I'm starting off with, 12 liters. If 2 additional grams of helium are added, so that is going to be my N2. And I have 5.3 grams plus 2 additional grams, which gives me 7.3 grams. Now, just like I did before, I'm going to have to change this into moles. So we can take 7.3 and divide it by our molar mass, and I get 1.825 moles of helium. That is going to be my N2. What is the new volume? new volume. So V2 is my question mark. So I need to get a gas law that just looks at pressure, oh, sorry, the amount, moles, and volume. And that is our first law right here. Moles and volume are directionally proportional. They have a direct relationship. They are directly proportional. So my equation is going to be V1 over N1 is equal to V2 over N2. And we are solving for V2. So V2 is going to be V1 times N2 over N1. I'm going to erase my V2 so they don't run out of room. Now we have our plug and chug situation. My initial volume is 12 liters, and I can multiply that by my final moles, my final amount, 1.825 moles of helium. And then we can divide that by our initial amount of moles, which we calculated to be 1.325 moles of helium. Now, when we plug that into our calculator, we can do 1.825 times 12. When I do that, I get 21.9. And then I can divide that by my 1.325. And I get 16.5 liters. Now, does this answer make sense? Volume and the amount, our moles, are directly proportional. I increased the amount of gas I have, so I should see an increase in volume. I started out at 12 liters, and then I ended up at 16.5 liters. So we did see an increase in volume.